and this video is going to cover Unit 1.1 and Section 1.2. I would suggest as you get started on this, it may be best for you to focus on copying the notes down in one setting and then going back and listening and just trying to understand separately. So 1.1's title is Moles and Molar Mass. So I want to remind you a little bit of what a mole is. So the mole is kind of a central unit in all of chemistry that we use in order to convert between other units. You're never going to go into the lab and measure 2 moles of something. You're going to measure in grams or milliliters or some other appropriate unit for mass or volume. However, you will be expected to convert between those using the mole. So I want to remind you that moles of one substance to another in a chemical reaction are in ratio, always in ratio. They are whole number ratios, right? And that goes a bit into stoichiometry, which isn't part of this unit, but I want to remind you of our mole kingdom, because it's been a bit since we covered this, right? Work with me here. Here's my castle, where my mole lives, right? My 1 mole. And there are 3 ways, right, in each mole kingdom in which we can make a mole. All right, so one of those would be particles. Another term for that would be atoms, or sometimes molecules. When we hear those terms, then we're going to be referring to Avogadro's number. So in order to convert to and from particles, atoms, molecules, and a mole, you would need to use Avogadro's number, which you would either be multiplying by or dividing by, depending on which way we're converting. Avogadro's number, just a reminder, is 6.02 times 10 to the 23rd power. Right, another way we can make a mole is a liter. Right, and it has a constant as well. That number is 22.4 liters, decimal there, are equal to 1 mole. Same scenario there. The third way we can make a mole is using grams. This one's a bit different because this is the only one where it's very dependent upon the substance. There's not a constant number that applies in a blanket to all substances. So this number varies depending on which substances we're talking about it. Why is that? Because each substance carries a different mass, right? And mass is measured in grams. So this is where we use something we call molar mass to convert between the 1 mole unit and the grams of said substance. All right, so I'm going to switch back to where we were. What is molar mass exactly? All right, so in 1.1, moles and molar mass is what we call grams per mole because it's equal to 1 mole, right, of a particular substance. How do we get that? Well, we get that from the periodic table. Right, that mass number, which is the decimal number you see in each box for each substance there, round it to 2 decimal places. We will always round it to 2 decimal places for this course. Okay, so your carbon, for example, would be 12.01 in this example of sucrose, right, which is your table sugar, which is C12H22O11. So we would take our 12.01, again, that's rounded, and we're going to multiply that by how many carbons we have, right? Each carbon weighs 12.01, so we multiply that by 12, we get a total mass of 144.12 for the carbons in the substance. Do the same for hydrogen, right, which mass is 1.01, 22 of those gives us 22.22, oxygen 16, 11 of those gives us 176. Now to get the total, we want to add all of those together to get the total mass of the whole sucrose molecule, right? So one sucrose molecule has a molar mass of 342.3. Now, if we were calling it molar mass, we would call it grams, right, per mole. If we're calling it a formula mass, right, or a molecular mass, we use different units, but I want you to know that those mean generally the same thing. The number isn't going to change, same value, just a different unit to represent it. So if you see the term formula mass, we're calculating this the same way, okay? The only difference in those would be the units. AMU stands for atomic mass units. That is a measurement we use generally when we're referring to the way that we calculate the average atomic mass, which is how we get that decimal number. It's a weighted average. We'll get to that in a bit. So that's where that comes into play. And you'll see that U there as well, which just represents units. Particles, back to where we were a minute ago. Remember, particles, atoms, molecules, all represented the same way. They're equal to 1 mole of the substance. That is Avogadro's number here you're seeing, 6.02 times 10 to the 23rd power. Oh, sorry about the add. All right, right there, and that is a constant, right? Different than our molar mass we were looking at a bit ago. So if we're using that same example and going through the same substance as sucrose right here, right? How many particles would be in 1 molecule of sucrose? 6.02 times 10 to the 23rd. How many moles would be there? 1 mole. Okay. What would the formula mass of that be? 342.3, because we already did that addition above. And we would use the U as the unit for that. And as I mentioned before, the molar mass, same value, different unit representation. It would be 342.3 grams per mole. Per mole meaning per 1 mole, right? It's understood 1 there. All right, moving on. A little bit of practice for you. If you were to stop and do the molar mass of H2SO4, which I would expect you to be able to do all day long, you should arrive at an answer of 98.08 grams per mole. Same thing for aluminum nitrate here. You should arrive at 196.01 grams per mole. If you don't get that, you're rounding incorrectly, right? Or perhaps you're multiplying things. We shouldn't. So, quick little review. On those H2SO4, you should be multiplying the hydrogen by 2. You've got a single sulfur there, 4 oxygens, right? And then doing the addition of those. Down here, do we remember what to do when we deal with parentheses? So here we have 1 aluminum. Okay. How many nitrogens do we have? There's a couple of ways to approach it. That 3 should distribute to each element listed inside separately. So there's 1 nitrogen inside parentheses, and then we have the 3 outside. So that leaves you with 3 nitrogens. Okay, then our oxygens there, we have 3 inside times 3 outside, which gives us a total of 9 of those guys. So you would multiply each of their mass values from the periodic table by those numbers. Alternatively, you could do nitrogen and the 3 oxygens together, get a total, multiply that by 3 that you see outside the parentheses. That's another option, give you the same answer. And that concludes 1.1. So moving on to 1.2, we have mass spectroscopy. Okay, so first of all, what is this? Well, mass is referring to everything we just talked about, grams from the periodic table, right? The mass of a substance. Spectroscopy, right, is a reading, a printout, essentially, that we would use. Well, it's digital now on a screen, where we can determine the identity of a substance based on what we see as present in the masses. So it's able to kind of divide up the substances by mass and show us what's there, right? So this is done with a, well, I'll show you that in just a second. Let me roll them down, sorry. Let's start here. So remember I talked about a minute ago the average atomic mass that you see on the periodic table, that decimal number, not a whole number, it's always a decimal number because it's an average, right? So it's representative of all of the protons and neutrons, not electrons, they're not included, that's important, all right? So mass is protons and neutrons only, and there's a reason for that, right? So here's our atom, right? A reminder that we have a nucleus in there, and inside that nucleus we have protons, which are positive, and neutrons, which are neutral. I'm going to draw that as a circle, right, showing there's no charge there. Electrons are tiny, tiny, right, little beings that are outside that nucleus. Protons and neutrons are very heavy, right? They're considered to weigh essentially, rounded off, 1 atomic mass unit each, right? Electrons weigh a tiny, 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 tiny fraction of that. It's a really small decimal point with many, 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 many places out. So it is essentially, I like to compare it to if you're weighing an elephant and you place several pieces of fuzz on the elephant, does the elephant have a different weight now? Well, technically, yes, but you're not going to see that on the scale. It's not going to make a difference. Okay, so therefore we do not include electrons in our mass number. This is solely from protons and neutrons, which are all located inside that nucleus, which is very heavy, right, inside that nucleus, which is why we say an atom is mostly empty space, right, with almost no mass out there. All the mass is located in the central nucleus. So I want to remind you that there are different masses for an element, though. So there could be a carbon out there. Remember, you can't have 0.2 of a neutron. That doesn't exist. You either have a neutron or you do not have a neutron. So those numbers you see on the periodic table are simply averages. So a real life sample of carbon will have a whole number mass. For example, carbon 12. 12 means it has a total, right, sum total together of protons and neutrons that add up to be 12. Right. So that means, right, we're able to figure out the number of neutrons based on the proton number. The atomic number you see, which is the whole number in each box on the periodic table for carbon, for example, right, 12.01, and then we have a 6, right? That 6 is how many protons carbon has. Protons never change, right? It's a rule I tell you to go by. So that number is consistent. So if we're dealing with a sample of carbon 12, it would have 6 protons, 6 neutrons. If we're dealing with a sample of carbon 13, we've got 6 protons, 7 neutrons. All right, so that carbon 12 and carbon 13, those are called isotopes. They're all carbon, they're just different forms. They have a different mass. They have a different mass because they have a different number of neutrons. So the mass spectroscopy is able to show that to us. We're able to see on these readings from the spectrometer what those different isotopes are in a sample that we put in there. Where do you get a sample? Anywhere, right? Out of the ground, anything that you bring in, we can do. Where do we see this commonly in everyday life? Drug samples. Yeah, so say someone gets pulled over by the police. They see a substance in the car that is suspicious as being an illegal drug. They take that sample, send it into a lab. We use mass spectroscopy to identify what that substance actually is, right? And whether it has the right makeup to be an illegal drug in order for that person to be prosecuted. Okay, that being said, how do we arrive at that decimal number? We know there are isotopes. We take an average of these isotopes to get that decimal number we see on the periodic table. This is a common thing I'd expect you to be able to do and memorize how to do. So I give you an example of lead here. We're looking at different isotopes of lead, just like I gave you examples of carbon. You've got lead 204, lead 206, 207, and 208. Okay. Now we look at the abundance of those. What does that mean? That means how much of it actually exists in the sample. For the periodic table, we're looking at how much of it on Earth exists. Right? How much of the lead on Earth is lead 204? Only 1.37%. That's a small amount, right? Lead 206, 26%, 20% for 207. Finally, 208 is 51%. Which of those is the most, right? Lead 208. So I can go ahead and make a prediction before I do any math and tell you there's probably more lead 208, right? So that average should be closer to 208 than it would be to say 204. But because that's the last one, there's no number bigger than 208. I know the average is going to be probably just a little less than 208. So that's a solid prediction that I can make based on logic from the numbers that I'm seeing. So to make this make a bit more sense, this works very similar to your grades. So remember how your tests are weighted to a greater percentage than, say, your homework or daily work in classes. So therefore, your overall average will be closer to what your test average is than it will be to, say, those smaller percentage values like the homework, right? So that is the same process we use here mathematically to determine those things. Well, how do you actually do that math? I'm going to show you real quick. In order to calculate this value here, which is the total average atomic mass, 207.2. You're going to remove the percentage sign, right, of each of these by taking the decimal and moving it 2 places back to the left. So I'm going to take 0.0137, right, I move that decimal back 2 places from the 1.37%. I'm going to multiply it by the mass given, which in this case is 204. I'm going to get an answer. Right? And I'm just going to call this answer 1. All right, I'm going to do the same thing for 206. I'm going to say 0.2626 times 206. Right, answer 2. All right, I'm going to do the same thing, 0.2082 times 207, answer 3. And lastly, 0.5155 times 208, and I'm going to get answer 4. Oops. Okay, I'm going to add all 4 answers together. And you do this for how many you have. There are 7 of them, you add 7. There's only 2, you add the 2. And then you will get your final answer. which we call the AAM, or the average atomic mass. Okay. The total thing, or in your case, your final grade. So those work in the exact same way. All right, moving forward. A little more on our mass spectroscopy. So let's talk about this machine, right? The spectrometer is the name of the machine. And there are several machines we're going to talk about in this course, and quite a bit in this unit and unit 2. So in science, instead of calling them pieces of equipment or machines, we like to call them instruments. Right? They are very delicate, right? Like an instrument, something to be used great care with. They're also very expensive. So the spectrometer is an instrument that weighs and counts. So it counts how many carbons, for example, and weighs the masses of those carbons present. So this allows us to determine every single isotope, right, that we see and the abundance of those isotopes. And these help us to arrive at those numbers I just showed you an example of. So a couple of different ways you'll see these axes labeled. So generally on the bottom, you're going to see a mass number, right, and it will be a whole number. This one is boron, in example 1, and it's showing you that we have boron 10, 11 present, only 10 and 11 because that's the only place that we're actually seeing any spikes, right, on our graph. And then you'll see a relative abundance here, right? And oftentimes you'll see, rather than it having an exact multiple marks on your axis, it's a little hard to read. So they tend to put it here, right, just above it, rather than marking it here, because they tend to be odd numbers that are a little difficult to show. So that's something you'll often see. So how do we figure this out? From here, this is all the data you'll be given, and you'll have to do the math on your own from here. So what do I determine from this? Well, we have boron 10, and I have 23, right, as our relative abundance. Boron 11, and I have 100 as our relative abundance. So what does that mean? That means that our machine counted a total of 123 atoms of boron. Okay, so how do I make that into percentages so that I can do the math that I showed you a bit ago? Well, I'm going to take each one and divide it by the total. So for boron 10, 23, right, out of a total number of 123 atoms that we saw, right, were boron 10. So when I divide those, I'm going to end up with 18.7%. So when you do the division, your calculator is going to say 0.817. In order to make it a percentage, you need to multiply by 100. So that would be, right, our percentage of boron 10. We can see that obviously 23 compared to 100, the majority of our atoms are going to be boron 11. So we're going to take our boron 11, 100 out of 123, gives us an 81.3% abundance. Again, you would have to multiply that by 100 once you put the number in the calculator to turn it into a percentage. So now that we have that, we can take those values and represent them as percentages on our chart. Sometimes it will be represented already as percentages for you, which saves you that extra division step. Sometimes they're going to expect you to be able to do this without the percentages. So we need to be confident in adding that extra step if it's not given to you. So now we know that boron 10 is 18.7%, as we calculated boron 11, 81.3%. Now to calculate the average atomic mass, which I showed you in that previous example with the carbons that we were working on. Excuse me, the leads that we were working on. From here, you want to take your 0.187, right, because we want to change that percentage to a decimal. We do not have a percentage button on our calculator, so you've got to manually change that in order to do your math, right? And we're going to add it together, right, because we always add all of our individual answers together to the 81.3% of boron 11. We get a total of 10.8 atomic mass units. If you were to look at your periodic table right now and look at boron, you're going to see that the average would be 10.8 AMU plus a few decimals there, but we like to round to 2. Okay, so let's talk about example 2, where we are looking at a similar readout, right, from a mass spectrometer. We have 4 peaks at 90, 91, 94, and 96. So what conclusions can we draw without doing any math? What can we determine? Well, we can determine there are 4 different isotopes present. We can determine that there is no zirconium-95. It's not present. I see that there's no mark there, so there's nothing there. I would expect the average mass to be what? What are you thinking? I know that an average has to fall somewhere between, right, the beginning number and the end number. So I know our average has to be somewhere between 90 and 96. Well, which of those isotopes, right, has the greatest relative abundance? From looking, I can see that 90 isotope has a much, much higher abundance as compared to the others, right, in the sample. So I'm pretty positive that our number is going to be much closer to 90 than it is to 96, right? And that's a fair assumption. So if you're looking at a multiple choice question, you can automatically rule out some of those higher values, right? Anything outside of 90 and 96 range, you're not going to see anything there. And anything up to 96, we know we're going to have those lower numbers, right, or a higher weight and higher percentage. So those are going to be your best options. So those are some conclusions that you should be able to draw quickly without having to actually do any math. And that concludes our lesson on 1.2.